In this video, I will explain the difference between collisions that convert reactants to products and those that do not in terms of energy distribution and molecular orientation. I will be using science practice number 6 to explain how collision theory helps to differentiate effective and ineffective collisions. Collision theory explains why reactions occur at different rates and ways to change the rate of reaction. Collisions refer to reactant molecules approaching close enough to disrupt existing bonds and encourage new ones to form. I will be using science practice number 1 to show the difference between effective and ineffective collisions through 3D models. In the purple cup, we have white vinegar, also known as dilute acetic acid. In this yellow cup, we have baking soda, also known as sodium bicarbonate. Here we see no chemical reaction occurring because the reactant molecules are not yet colliding. However, when we allow the molecules of the two reactants to collide, a reaction occurs. This is because collision theory states particles must collide in order to react. Sodium bicarbonate and acetic acid react in a double replacement reaction, thus forming carbonic acid and a conjugate base of acetic acid. In addition, carbonic acid will break down into water and carbon dioxide in the presence of water. However, only a small percentage of collisions are effective collisions. Two factors that determine effective collisions are the orientation of the molecules and the energy distribution, also called the activation energy. Orientation refers to the lineup of atoms during collisions. When molecules react with proper orientation, it allows the colliding atoms to form bonds and break their original bond. We can see that the sodium collides with a single bonded hydrogen, causing a double replacement reaction and thus a chemical reaction. If molecules collide without proper orientation, electron repulsion will cause the molecules to bounce off without reacting. Although molecules collide with correct orientation, if there's not enough energy, the molecules will not react. Here, I will be using science practice number 7 to connect to thermochemistry, specifically exothermic and endothermic reactions. Here is an exothermic reaction diagram. The difference in energy between the reactants and products refers to the change in enthalpy. The highest point on this diagram is called the activated complex or the transition state. This is where there's a likelihood whether the activated complex forms products or remains as reactants. The difference in energy between the reactants and the activated complex is called the activation energy. The activation energy refers to the minimum energy reactants need to form products during collisions. The kinetic energy of the molecules plays an important role because the activation energy is provided by the collisions between reactant molecules. The sum of the kinetic energy of the reactants must be greater than or equal to the activation energy in order to reach a transition state. If molecules collide with sufficient energy, a reaction will occur. If the reactant molecules do not possess enough energy, the molecules will just bounce off of each other without forming any bonds. To increase the reaction rate, we can increase the concentration of reactants, the physical surface area, the temperature, or use catalysts. Here is a Maxwell-Boltzmann diagram which defines the speeds of gases at certain temperatures. This barrier refers to the activation energy. When the temperatures increase, we can see that the distribution of energy amongst the molecules increases. At higher temperatures, more molecules have energy greater than the activation energy, resulting in more effective collisions. Their main function is to provide an alternate pathway for a reaction with the lower activation energy, thus increasing reaction rates.